In our lecture today, we're going to talk about the effect of the oceanographic environment on the selection of the offshore structure for oil and gas production. Okay, so say offshore structures for oil and gas production. And we are talking about the effect of the oceanographic environment. Okay, that means and more specifically, we are talking about wind, we're talking about waves, and we're talking about current. And we're going to see now this has an effect on how we design the structure. We have to design it considering the characteristics of wind, waves, and current of the place where the structure is going to be located. But also, we are going to see, I'm a bit more interested to see that each location has some characteristic uh, wind, wave, and current. Okay? So that affects in a way which kind of structure I'm able to choose, and I have to be careful on that respect on some things. But so um, yeah. So the first thing is just to define it. If we have an offshore structure, it might be floating, it might be just fixed to the bottom. Okay. That offshore structure okay, typically has three main components that is being affected or loads that cause loads on this structure. So one of them is the wind. Typically we have a profile like that due to the vicinity of the sea level. Okay. Then we have current that also we have a profile which is also a bit like that. Okay, and finally we have, I'm not sure exactly how to plot it, but maybe we can make it like that. And we have waves, which are variations of the mean level height that propagate in one direction, and they impact the offshore structure and they cause a significant movement. So this wind, waves, and current have to be taken into account in the design of the must be taken into a, must be taken into account when designing the offshore structure. Okay, and essentially we have three ways in which, or a few ways in which they are taken into account. Okay, well, one of them is the location of the flare. And here is very important the wind location. If we say we have the offshore structure like that and we have our flare here, we want to avoid to have in most of the cases that the wind is flowing against and bringing the smoke to the platform. Okay, the plume of smoke to the platform. Okay, so one of the things that we have to take into account. The other thing is the deck elevation. Okay, and that's related to if we have, for example, a spar. Let's use a spar as our example. Okay, and we have our sea level here. Okay, we want that the wave, the most critical wave or the biggest wave we can have, and that's usually done in a lapse of 100 years. It doesn't reach the deck. Okay, it doesn't have the chance to reach it cannot, the deck, we make it high enough such that this wave cannot reach the deck. Okay, so that's what we call like 100-year wave. Okay. Some other things are taken into account in the design. It's we make it for a design wave. Okay, we are going to see now, but we design our structure for some design characteristics which are going to be the most frequent wave, okay, and for a range of periods. Okay, and we're going to talk a bit now, but for a range of periods. And we're going to see now what that means, but essentially we have a wave, that the wave has not only an amplitude associated, but it also has, or a height associated, but it also has a period. So we make a design which is the most frequent, okay, the most likely in the area, okay, and but the period can be changing significantly usually, so I just do the analysis for a range of periods and design my structure on that with those conditions. Um, then the next one is the storm, and this is typically 100-year storm, to see how well is going to weather the structure on this 100-year storm. And then I take uh, relevant values of magnitude and frequency. And the next type of design we make is a long-term variations. Okay, and this means the fluctuations we have during the life, let's say in the 20, 30 years, 10 years that the platform, the offshore structure is going to be operating, and these have to do more with fatigue considerations. Okay, remember fatigue, if we take like a clip, a metal clip, and then we start to bend it several times, at one point we're going to break it. So we have the same effect in offshore structures. If we have a load that is impacting with certain frequency or during a long period, we have to be sure that we're not going to have any failure due to fatigue. So offshore structures they exhibit movement depending on the force marine loads on the structure. And if we're going to make a simple diagram of how this looks like, we make like a function, okay? So our structure we have, okay? Then on the structure we have the input, we have forces, marine load on the structure. Okay, and these loads are typically going to be changing in time. They are a function of time. And what we say here is essentially is the magnitude, okay, and the frequency associated with that load. And also sometimes we have also the direction. Okay? And the output of that structure is going to have movement. Okay, it's also going to be a function of time, and you also have the stress, mechanical stress on the structure. That is also going to be a function of time. Okay, and essentially when you look at the stress, okay, you're limiting movement because a higher movement, usually a bigger movement, causes a bigger stress. So you want to reduce the movement, but essentially you want to look at the maximum stress and also the fatigue, okay, the fatigue design. What we mentioned, we have a closed that act on the structure for a long period of time, so this can cause fatigue. Yeah, just as one example, so we're going to see, we're not going to go into the design of the offshore structure, okay? But these are things we have to take into account when we design, okay? And some things that I mentioned here is the location of flare, depending on we are going to place here the wind direction, okay? And there is usually, we're going to see now the wind is varying in time, location, magnitude, direction, but we want to avoid that if most of the wind most of the time is coming from this direction, we want to avoid to put the flare against the offshore structure, deck elevation, okay, because we don't want the biggest wave we can have in a period of 100 years, which is our kind of period design that won't reach the facilities, won't reach the upper deck. And then also we have these things that essentially they are to design my structure in a way that it can withstand the marine loads, okay, what we call the oceanographic loads. Okay, but as one example, one of the main challenges we have is that these wind, waves, and current, they are typically varying with time. Okay, depending on the season of the year, depending on the year, depending on the uh, atmospheric conditions, then these are going to be changing dramatically with time. So that's one of the challenges we have. So my intention in this lecture is simply just to not to make you experts, but you're aware of some of the issues we have to take in consideration when designing offshore structures. And particularly, how do you read or how do you cope with the variability of these marine loads? And the second point is to make you aware that offshore structures they are vulnerable to some conditions, to some particular excitations. Okay, and I think we're going to go to the second point first, okay, which is that if we excite this structure, okay, we see that these are like excitations, the forces and the marine loads. If we excite this structure in some particular region, okay, in particular with some particular frequency, we're going to get high movement, okay, and that's something. If we say the structure is a mechanical system essentially, okay, we see that, and for that, let's play a video. It's see if I find the mouse. Okay, from Missouri, Professor Kwong. I found it on YouTube. But essentially, what is happening? You have a structure which has two columns. Okay, three structures that have two columns, and they have one mass at the top. And then in this experiment, the base is being oscillated back and forth, okay, right and left, with different frequencies, okay? So you see, initially we start with very long periods. The wave is going very, very slowly, but then we start increasing and you start to see some appreciable movement on this structure to the right. Here we can accelerate a bit the video. Can you see there comes a frequency? If I start increasing that frequency, if I start decreasing the period, you see that you start to have big oscillations on this structure, okay, big movement. So that means that its resonance frequency, okay, it's is very vulnerable at these 4 hertz. Okay, if I excite this structure with 4 hertz, is going to exhibit maximum amplitude, maximum movement, and we probably will have also big stresses. You see here the columns, they're actually quite deformed. Okay, but the other structures are not affected that much by that frequency. Okay, by that frequency. If I go further, if I start to increase it even more, okay, then the structure to the right stops moving, and then the structure to the left starts to move significantly. This the structure in the middle. Okay, at 6.35 it exhibits the maximum amplitude and also probably the maximum stress, which if you're going to be operating that structure, you want to avoid. If you want to put that building or that structure offshore, you want to avoid frequencies, excitation frequencies that are 6.35. Okay, and finally we go to the last one, which is much higher. So we had 4, 6. This one is 11.35. Okay. So the point is here that each structure, depending on its characteristics, okay, will have um, what we call a natural frequency, okay? Each structure, depending on its characteristics, okay? And the characteristics we are talking, if any of you took any course in mechanical engineering, we have essentially, we can model all of these systems, usually with a spring, and we can put a dampener, and we can put a mass, okay? So this is, in a way, the inertia, the mass. We have the flexibility, okay, which is the spring constant, and then we have the dampening, okay? We'll exhibit a natural frequency that, if excited at this frequency, might exhibit maximum movement and stress. Okay, what we call the natural frequency. That's like a term we have. So for offshore structures, we have, for example, some structures it's relatively limited the movement they can have. If we talk about a jacket, okay, we can say an analog of that is maybe a bar which is uh, drilled or is located. It's fixed to the ground. Okay, so then you have some movement maybe in this direction due to the excitations that you have. You might have on the wind and the current, so you exhibit a movement just like a fixed bar. Okay, while if you have like a floating structure, okay, in floating structure is a bit more complex. So you have, if we say in the most general case, is like a ship, okay, or an FPSO. We're going to have essentially a very important movement. We have to be careful. I told you it affects risers, it affects if we have dry Christmas trees. We have heave, okay, moving up and down. Then we have moving front and back. This is called surge. Okay. Moving side to side. This is called sway. Okay. Okay, and then we have also, besides this movement in the, would say, the vertical, back and forth and right and left directions, we also have yaw. I'm going to use a different color. Okay. We also have roll, which is this movement, very important, that might cause significant destabilization of the vessel, roll, and then we have pitch, okay, which is the rotation in this direction. Okay, pitch. So when I talk about movement, in fixed structure, okay, it might be, we know like there are limited movements you can have, but it's essentially might be the movement of the platform back and forth. Okay, but if you're talking about a floating structure, essentially you have a variety of movements the structure can exhibit. So you have to be careful to discern exactly what 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 movement are you talking about. So just to give you, besides the example that we had before, I can show you maybe, find the figure. Okay, some of the natural frequencies or some of the natural periods, remember frequency and period, okay, of some vessels that I have. I took this figure from a presentation given by Equinor, okay, and then I modified myself just that I'm able to use it. But essentially here you have on the y-axis you have uh, the the period of different um, excitations, type of excitation. So you have waves and wind. Current is not here, but you see wind is actually quite high, um, quite long excitation period, big excitation period, while waves is actually in this range. But be aware that the scale here is logarithmic. Okay, earthquake you have also. But you see, most important to the right, you see first you have for different um, types of offshore structure, you have its natural periods. Okay, so you have jackup, and essentially if I make the jackup a bit longer, that means if I make this bar much longer, then it will have a different excitation period, natural period. Okay, so that's why this water depth tells you that it has some variation with water depth. If you talk about a jacket, okay, because remember the jackup has um, like the same cross section while the jacket is getting wider and wider. Okay, it has a different line. So with more water depth, you're going to have the natural period is getting larger. Okay, in this case, for like 4, 5, and when you are at a shallower water depth might be 2. Okay? TLP, we also have a big effect on the TLP. Remember, it has a big effect on the depth because the TLP has these tethers or tendons, okay, that are keeping it fixed to the bottom of the ocean. And then if you make this very long or very short, it will also have an effect, okay. And here you see essentially it's telling you the movement, okay. In this case, the jack-up and jacket, I told you there is usually one movement that you want to uh, that is important to check. But on TLP, you start to look into heave, roll, and pitch. Okay, heave, vertical up and down, roll and pitch, and these are the natural periods. If you excite this structure, then you will have this maximum peak, maximum amplitude. Then you have here at the top other structures that they are floating, okay, so they don't depend on the water depth too much, okay, but you see semi-sub, again the 3 has excitation periods that are on the upper end of the waves, okay, and spar heave also has periods that are quite high. Okay, so that's simply a very simplified diagram, but just to show you um, how each structure, the natural period of each structure, how does it change of each particular movement that I'm interested in, how does it change with depth, and how does it overlap with the excitation, okay, which is basically wind, waves, and current. To make it a bit more quantitative, okay, we can something that is sometimes made. So the movement and stresses is calculated on the structure using either numerical models, simplified numerical models, complex numerical models. Um, you use sometimes models in a pool. At NTNU, we have at MarineTech a pool where we can make tests when we measure the movement of scaled down models of offshore structures. Okay, but I'm just going to show you like one of the results that is used often. Okay, so we use a graph. It's called response amplitude operator. Okay, they have models that they can run with different input, and they can predict the movement with different variability, with different uh, conditions of the excitation. But essentially, this is one of the results that is often used. It's called a response amplitude operator. Okay, called RAW, abbreviated RAW. And this operator is basically the amplitude of the response, okay, divided by the amplitude of the excitation. And essentially here we're taking if it might be, for example, the heave. Okay, remember that we are talking about these particular movements. Okay, if you have fixed structure, if you have a floating structure, you have heave, you have roll. So is that amplitude, okay, of the heave, and usually it's a value in meters. It can be divided, for example, by the wave amplitude. We haven't talked much about waves, okay, but remember if we visualize a wave in time, okay, it might be like a sinus wave. Okay, so this we call the elevation, okay, and then we say it's a sinus. Okay, so we are saying the amplitude, okay, for example, that's amplitude. Yeah, and then we have the period, okay. So we create that ratio and then we say, well, if a wave, let's say the rho is 2, okay, so that means that if a wave with 1 meter is impacting the structure, you're going to get a heave of 2 meters. Okay, you're going to get a response of 2 meters. Okay, so we make a plot of this rho, okay, which is a dimensionless number. Okay, but we put the units here versus period. Okay, or we can use also frequency, but we use period in seconds. Okay, and we see how is the response of a given structure. Okay, and I'm going to show you just some plots that I took from some books and some theses. Okay, so you see, just keep one curve. Let's maybe look at this curve that we have here. Okay, this with this the dashed line, a bit thicker. Okay, which you see how it changes with the period, with the excitation period. So essentially, you see is exactly what we saw in the video. That for some periods you have very low rho. That means if you go with a wave of 1, you don't get much heave. Okay, you don't get much vertical movement. You get like 0.25. Okay, but then if you start increasing the period, okay, that means if you reach close to 20, then it's going to change dramatically the response. You're going to get 1.2, okay, well 1.75 or 1.8. Okay, and this is the peak that we were referring to before, that you have each frequency has a natural, each structure for one particular movement has a specific natural period. Okay, so you see these peaks here. For example, this peak is quite exacerbated, and then you see the different vessels. Okay, you have semi-submersible, you have spar, you have a drilling ship, and you have an FPSO. Okay, which the FPSO is a bit flat, like this. Let me show you a few more. that it's for the Ceban, the heave, rho. That's also taken from an SP paper, but essentially you see that the Ceban that is used for production in Brazil. So you see the rho function and you see the period, and you see clearly that in this case we have a peak for the heave in around 12. Okay, and you see some comparison between model tests that they make on a pool, numerical models, and then also monitoring of the structure. Okay, but this means that that structure is particularly susceptible to this range of periods. Okay, so if this peak causes significant displacements that we don't wish to have, okay, because they cause maybe structural problems to the riser, or they cause some operational problems, or they cause simply too much stress on the structure, then we don't want to be using that particular structure on that region, okay, on that location. Here there is another plot which is interesting. And it tells you the same plot, the rho versus the period for different types of structure, okay, but also tells you the range that we have in our particular location. Okay, you see that's the Haltenbanken region, which is just offshore Trondheim, and you see that most of the waves they are actually centered around, and we are going to talk a bit how do we get this plot or how do we get this trend, but essentially they are centered around 9. Okay, but you can have, of course, waves that are have long periods. Okay, um, that it says here is supposed to be a winter storm, or we can have also very low. So we can see depending on the peaks are in this region. That means that we, in principle, will have okay um, response, or we will have moderate response of the vessel. Okay, unless maybe we have this green one, which is I don't know what it is. Okay. But also one thing important to mention here is that you see you have H6E operation and H6E survival. So it's the same structure, okay, but essentially they have different characteristics. The way they change it, for example, is with the ballast. Okay, so in normal operation, you have maybe some ballast level. You are above the sea level by some meters. But then in survival, you change the ballast such that you try to make the structure more stable. Okay, so you see the difference between the black and the gray, okay, the gray with dots, which is this one here. Okay, so there is some difference. Okay, here you have more. For this, you have more raw. Okay, but here you have less. Okay, then you decide um, if that structure is suitable or not. Okay. Then the last thing I want to show regarding this row diagram is this. You see you have the row on the roll also. In this case, the roll is not you don't measure it in meters, but you measure it in degrees. Okay, so you see you have the vessel, and this IART is anti-roll tank. Okay, so you see that without the tank, you have actually this row of limited, okay, to maybe 6 or 7. But if you don't have this tank, then you can have this very high peak, okay, which is essentially like 4 times the value of the row if you had the anti-roll mechanism. So just to show you also that this row can change depending on some design of the structure. Okay, so I can modify slightly the frequency by making a better and a smarter design. Okay, so now that we have seen that, and you see that it's some structures are susceptible for some, in particular, some range of frequency or some range of period. Okay, remember the frequency is simply we make it with the letter F and is 1/T. Okay, okay, and this is essentially is cycle per second. Okay, we complete one cycle in per second. Is the number of cycles I complete in a second. So let's talk a bit now, the first part that I was discussing, that is essentially we discussed about the response of the offshore structure, okay? But now we want to see how this wind, waves, and current, how do we take it into account its variability, or how do we, because that's the essential point, right? We know that each each structure will be affected differently depending on the excitation. Where is the mouse? Depending on the excitation. So we want to know exactly how to characterize that excitation. Okay, that's like the second part of this lecture. Okay, so let's get very quickly. So wind and currents, they're usually considered like fixed. You have to be careful a bit with the direction, but essentially you can assume for your calculations that they are on a fixed value. Okay. One thing that is important with wind, I'm saying now on the design, okay, but one thing that is important with wind is the direction. Okay, and that, for example, some diagrams that are used for it is this is a wind rose. Okay, we call the wind rose, and essentially the color tells you the first is the direction from where the wind is coming from. Okay, so you see that in this case, in this particular location, there is a tendency of getting more wind from the southwest, okay, or from the west, where between west and southwest. And you see also how that wind is split, okay, from all these are all the measurements that I have made, how that wind is split. Okay, so for example, from this direction, there is a big part of the wind that is in the range between 2 and 16 kilometers per hour. But you have also some that are between 16 and 40, and then you have finally 40 and 55. Okay, and the share, for example, if you go to this direction between south and southeast, then you see that actually you have more winds in the 16 to 40 range. Okay, so these are some things that have to be taken into account, especially what I mentioned before about the flare. Okay, so current and wind, so let's call it here, wind and current are typically assumed constant, but using uh, but and using sorry the maximum value. Okay, wind not wind but the wind direction also must be taken into account. But one very critical marine law that people have to look very carefully into is a wave. Okay, waves. And essentially waves, like I mentioned to you before, waves are, if we talk about the elevation, okay, we use this strange zeta letter in meters. Okay, and elevation is essentially the amplitude. Okay, we can have um, a very erratic. Okay, we don't say it's not periodic, it's not perfect like a sine or cosine, but essentially we have a very erratic, okay, signal, okay, with time. Okay, and that's what we say. That's the mean sea level, okay, on that particular region. Okay, so how do we deal with waves? Okay, so essentially waves, we have this famous mathematician, okay, that we say, well, no matter which signal we have, we can express that signal has a sum of sine and cosine. functions. Okay, and that mathematician was a French mathematician called Fourier. Okay, that essentially tells you that any signal, okay, can be represented as a sum of, and depending how many terms I need, depending how is the signal. Okay, if I use, maybe the signal is too complicated to capture only with two terms, I use more and more terms. Okay, and I can have 100,000 terms here, or I can have only a few, depending how different the signal is from a sine and a cosine. Okay, but essentially I can reproduce any signal with sum of sine and cosine. Okay. And I'm going to use this formula, which is slightly different. Typically, you use either the exponential with a complex exponent, okay, Euler notation. You can use a sum of sines and cosines, but I'm using here um, this expression using the phase shift, okay. That's the phase shift for each component, okay. This is the amplitude of each component. Okay, in our case, this will be in meters. Okay, and then you have this frequency, that's angular frequency, omega, okay, I, which stands for is 2 pi fi, okay, and that fi is the frequency. See that the units of wi are radians per second, okay, and to make the conversion, remember that the frequency is in cycle per second, okay, so you say I have in one cycle I have 2 pi radians. Okay, so that's the conversion I made on the frequency to convert it to, these two cycles are cancelled, and then I end up with radians per second. Okay, but it's essentially the same as frequency. So that tells you if I have this signal, I can maybe make that signal composed of different, for example, with time, I use one component which is maybe like this. Then I sum to that component, I sum another component which might be like this. Remember the shift, okay, so we might have this one starts over here. Yeah, and then let's say we have only three, because I don't want to be drawing until forever, but essentially you have one more, okay, that maybe looks like this. Okay, and at the end you end up, if I make all of these are going to be equal to the original signal that I was looking at. Okay, that's essentially what you are looking for. And the signal, original signal, might be something more irregular, okay, with time. And the main thing is that, so the first thing is that every signal, every wave, okay, that impacts the offshore structure, I can make it as a sum of different signals that are periodic, okay, that are pure periodic signals, like sines, cosines, okay. But how many terms I need, I don't know, but I know I can make this. And for that, I use something called FFT, the Discrete Fourier Transform, okay? Or I use also an algorithm called FFT, which is the Fast Fourier Transform. We're going to make an exercise on that later. So it's a mechanism. I input my signal, okay, and doesn't have to be, it's not a function, okay. If I had a function, an analytical function, I can simply uh, do it analytically, okay. But here I have a collection of value and the time, okay. I have a collection of points, is discrete, okay, because I have a series of values. Then I enter that into the FFT. Okay, and finally I end up with, and what I get is usually a plot that tells me in this range I have either the frequency or I have the omega, but typically it's the frequency, and here I have the spectral energy, okay, which is something that is proportional to the amplitude, okay, to this AI that we were mentioning above. Okay, but essentially this is saying that typically what we get is that, for example, we have very few components, okay, almost zero maybe for high frequencies and low frequencies, but then we start to have, for one particular frequency range, we start to have actually big a peak. Okay, so that tells you that there is a dominant. You call this peak, okay, this peak that we have here, if you apply the FFT. Okay, remember the FFT, the only thing it's doing is calculating these A's for all the terms, for all the range, is calculating the A's and the W, okay, or the F, which is the same. Okay, and then it's showing something like that when you apply the signal, and then it's saying it usually displays a peak, okay, peak, okay, and that's what we call the spectral peak period. Mhm. And that's in a way is the dominant. Sometimes people call it also the dominant period, the dominant frequency. Okay, well, that's not actually a period, but it's a frequency, but we make the inverse of that, then we get the period. Okay, so that means that most of the wave is dominated by that frequency. Okay, also one thing is that you can have, if you make, let's say, a sine wave, okay, regular, perfectly periodic sine wave, and you run it through this FFT, okay, you're going to get essentially frequency, you're going to get a peak, okay, simply one value. Because the signal is not composed of any other components. It's simply composed of one component at one particular frequency. You might have some noise, maybe, okay, some values around it, but essentially you have one big dominant frequency. So what we say, remember um, so that's what we use to cope with the complexity of, where is the mouse? I lost it again. But that's what we do with the complex to deal with the complexity that the waves have this complicated uh, behavior. Okay, so we try to calculate, use this FFT, and then we say, well, the most dominant. We know it's not going to be a perfect wave, but we are going to use the one that is the most dominant. Okay, so what we say to deal with the variability of the wave, of the waves in time, we say we apply the FFT on the signal and then report the spectral peak period. Okay. Okay, we assume that the spectral peak period, does not change. The writing is getting very poor, sorry for that. The spectral peak period does not change significantly in 3 hours. Okay, that's simply by definition, I say, and 3 hours is what I call a sea state. Okay. But statistically, we say, well, it won't change significantly in 3 hours. If I make some measurements in the first hour, second hour, third hour, it shouldn't change that much. If I measure, for example, in 5 hours, then you're going to have quite a bit of spread on this spectrum diagram. Okay. So that's how we deal with, so we try to split in 3 hours period, and for each 3 hours period, I apply an FFT on on the values, and then I try to report the peaks spectral period. Okay, but what to do with amplitudes? So what to do with amplitudes? Okay, remember that for example, for our raw response, okay, of the structure that we're going to look at, okay, we needed not only the period that we know already more or less how to get it, okay, but we also need to have the amplitude. So what do we do with the amplitude? The amplitude essentially we make a statistics on we apply statistics on we can apply on the wave elevation, okay, which typically, okay, like we have done in class, typically it gives you a curve which is a bit like that, and we have zeta here, which is in meters, okay, and is distributed, is usually a normal distribution around 0, okay, because the mean sea level will be 0, but then you can have values which are higher and lower. But one other indicator that they use instead of using wave elevation, okay, is wave height. And the wave height is, if we look at the wave, okay, the wave height is the distance, maximum distance between a crest and a valley. Okay, that's what we call by subsequent two consecutive crest and valley. Okay, distance between two consecutive crests and valley. Okay. And if you make a distribution, so you can look at the data you have, and then you can make a distribution of how the wave height for all the period, these 3 hours that you measured, how it looks like. Okay, so that gives you, usually it's a distribution that looks something like that. Okay, so this, remember, this is the PDF. Okay, and this is also the PDF, or if we have data, we will be a frequency diagram essentially. And this you call, okay, gives you something like that. Okay, and then you just don't report the whole figure because you have to do that for many 3 hours sea state. Okay, so essentially what you do, and that's a bit of a crazy approach, okay, but that's what is done. Okay, you have the H max that is ever recorded, and you have 2/3 of the H max. Okay, maybe it should be a bit closer, right? I think I did it too. Okay, and then on this period, in this area that you have here, you calculate the mean. Okay, and that mean, you call it, is a significant wave height. Okay, or HS. And that's the value I report for that sea state for those 3 hours. Okay, it's not the wave elevation because here is difficult. You maybe use standard deviation. It's not the maximum H max. It's not the most probable value of the wave height. It's simply that significant wave height. Okay, because it's like the worst wave that can occur. I don't use the maximum because that cannot occur all the time, but I use the mean in this range, from the 2/3 of H max to H max. By convention, simply by agreement, I decide to use that number. Okay. So now we have to characterize a sea state. A sea state, okay, which, remember, these are 3 hours. HS and TP are used. Okay. So one thing is that we can use here, there are equations. If I don't have, or I have a few data, I use Rayleigh, okay, distribution. Okay. And for the peak, sometimes for this distribution, sometimes analytical equations are used. Okay, and I just put the names. Let me just find them. Okay, and these equations or these distributions that we use is Pearson-Moscovitch. Moscovitz, or also one called John Swap. Okay, if I don't have data, then I can use some of these distribution. Or if I don't want to keep the data, the raw data, I can fit that distribution to the data. Okay, I can change the parameters of those equations to fit to represent the data. And also the same thing here, if I have some measurements, okay, if I have some points, probably won't look that pretty, but it will. Then I can try to change the factors in the Rayleigh distribution to represent my data. Okay, now data has to be, because from one sea state is not representative. You have to gather data. So data has to be gathered, wave data must be gathered for at least 2 years, okay, to obtain a representative sample of the conditions, of wave conditions in the area. To be able simply to have enough data. Okay, so how much is, if we take 2 years and we know we have 3 hours sea state, how many sea states, in a year? How many sea states are in 2 years? Okay, so we know that in a year we have, so 2 years, we have 365 days per year. Okay. In 1 day we have 24 hours. Okay, and then we have 3 hours per one sea state. So that gives me, if I make the calculation, two times 365 times 24 divided by 3, okay, 5,840. 2 years, 365 days per year, and 24 hours each day. and then I divide by 3. Okay, so 5,840. Okay. These measurements are made, for example, measurements are made from tankers, from merchant ships. They make it from neighboring platforms. They make it from meteorological stations, Coast Guard ships. They usually have some instrumentation to measure it. And instrumentation are, for example, buoys, floating buoys. They have lasers also, sometimes in the legs of the platform and on the boats. They install these lasers that they are measuring, okay, the wave level. Okay, so if the company either has to acquire the data of the region, okay, which it might acquire from a secondary company, or has to be profit or exploit the data that it has from existing facilities. Okay? So one thing that is done, so for all sea states with all measured data, okay, compute TP and HS, okay, for all. Then we make a diagram, okay, that is called a scatter diagram. That's the way I present, and you will see this in many field development reports, okay? This is called a scatter diagram of long-term wave statistics. Okay? And what we do is we put the TP, okay, and we put in beans, okay. We say, for example, from, let me just use real values, okay, in seconds. So it's like a frequency analysis, but made on a two-dimensional space. Okay, so we can have, for example, from 0 to 3 seconds. Then we have from 3 to 4 seconds when if they are in that bin. Okay, then we have 4 to 5, and then we continue like that. Maybe we go all the way. The periods we can have, you saw it from the diagram, but maybe, for example, 24, 25 seconds. Okay, so we create these columns. Okay, we split in beans. Okay, so these are like the beans of TP. Okay, let me just make it like that. These are, let me just write it here. These are TP beans, okay, for the frequency diagram. And then I create another column here to the left that is called the HS, okay, that will be in meters. And here again, I create again beans for the significant wave height. Okay, for example, I have 0 to 1, okay, 1 to 2, and so forth until maybe I reach 17 and 18 meter wave. Okay. So it's like a two-dimensional frequency or bean. Okay. Here we have our beans. Let me just move it to the right. I think I have space. Beans in HS. Okay. So then I start to, something didn't move here. Is I think this one. Okay, so then I have to count, I have to start to classify all the data that I have. Okay, in this case, if I have 5,000 data points, okay, so then I have to start to characterize where they're going to fit. Okay, so then I classify each data point I have in each box. Okay, so you count one TP, HS, maybe you have one here, then you have one here, then you have one here, but after some point of these 5,000 or more, you should have also maybe more, you start to see that some of them repeat. Okay, maybe you have more in this region. Okay, and then there will be some that you have very few. Okay, for example, very big waves you maybe have once in a while, or you have recorded maybe once or twice. Okay, but while waves that are maybe a bit smaller, but they have, then this one will be repeated quite often. Okay, so at the end, you end up with a diagram that looks a bit like that, and I'm going to show you. If I see where the mouse is, okay, with a map that is like that. And here with color is those cells or those combinations that have the most, okay, that occur the most during that period. Okay, so you have, for example, in this particular case, this is for the area where Ostahanstein is. You see that the most frequent waves, they are between 1 and 2 significant wave height meters and between 8 and 9 seconds. Okay, but you can also have quite spread on the period. You have that they go from maybe 6.5 to 11 and 12, and for heights between maybe 0 and 5 meters. Okay, so that's the most likely or the most frequent waves they have those characteristics. Okay, if you take a split on one particular, let's say I'm looking at a line. Let me see which color to use, maybe this black. Okay, I'm looking at a line here. Okay, for a fixed uh, wave HS. Okay, then you're going to obtain a PDF that looks like, okay, you have a center someplace here. Okay, and then you're going to have to go down. Okay, and you can also have, if I make on this particular line, okay, for a fixed TP, okay, this will be TP, okay, the variation of TP, and then you have also something similar. Okay, but that simply tells you for your C what are the most likely value to occur, and also which so the TP and HS that is more likely to occur for your location, okay, and how likely they are to occur. Okay, so you see that, for example, these waves so big with a period of 0 to 3, they never happen. Okay, they were never measured. You see here in this case they measured 292,172 sea states, okay, which if we make our calculation, this is how much? 292,172 divided by how many sea states did we have in a year? It was in 1 year we have 2 for 20, okay, half of that, 2 for 20, and these are states in 1 year. Okay, so that gives me quite a lot of years. They had to be measuring this data, or they had different sensors that they were measuring in the same period. 292,172 divided by 2 for 20. Okay, 120 years. Or, yeah. Okay. So that's all next we're going to make an exercise, but that's all I had to say regarding theory for this on about this topic. Bye bye.